Hello, welcome to EGN 3613. In this session, we will address non-equal payments that might be applied to the account. We will start with the gradient series. The gradient series is a gradual increase or decrease of payments. As shown in the figure, the payments increase as a multiplier of the factor G. As you can see, it's G, 2G, 3G, and so on until it goes all the way to n minus 1G. To find the value of the principal amount of the present value, we can bring each payment back to time 0. And this is the way that we used to do it before. Each payment, you can bring it back to 0, and you can use the calculation that this was a future amount that's been brought to present, and you can do it from there. Doing that for all payments can be actually expressed by a formula. Instead of doing each one individually, we can actually do it in formula, and the formula will be P, which is the present worth, and that's the present worth, is equal to G, and that is the factor, or that is the multiplier, the constant increase, multiplied by 1 plus I to the power n minus I n minus 1 divided by I squared multiplied by 1 plus I to the power n. And this value, we call it gradient series present worth factor. Gradient series present worth factor. So all this factor is called the gradient series present worth factor. And of course we can write it in a different way, which is P is equal to G multiplied by the factor, which is P given G with I and N. P given G with interest I and a number of periods N. Some payments could be a combination of two series. In these cases, we can separate the two series before we do any calculations. Then we can perform the calculation on both of them separately to find the present worth, and we add the present worth from each series or from each payment to find the total present worth. Let's look at the following example. In this example, we need to calculate the amount of money that we need to deposit today, which earns 12% annual interest if it was withdrawn as shown in the figure here. The first year 1,000, the second year 1,250, the third year is 1,500, the fourth year $1,750, and the fifth year $2,000. Now remember that I can see an increase, a certain amount increase in the payment over the years, which is from 1,000 to 1,250, that's 250, and then from 1,250 to 1,500, that's 250, and so on. So we have a gradual increase in the amount as we go. And if you calculate one from the first payment, which is the 1,000, so you can consider the G as 250, then this amount is 2 times G, and this amount is 3G, and the 1,000 is 4G, and so on. And this gradual increase that we talked about in the first slide. Now let's see how this could be solved. So in this example, we have the following payments. And here, or at time 0, I want to find the present worth. This is times 0, and then at time 1 we have 1000. At time 2 1250. At time 3 1500. At time 4 1750, and at time 5 2000. So the way to do the calculation for this one, we have 12% interest. So the way to do the calculation, as we used before, I can bring this one, do it in red. I will do the first payment as a future value, and I can bring it back to the present. So we need to find P using the formula for the future, where we have interest rate of 12%, and that's 0.12 n to the power minus n, and here in this one we have a 1 period or 1 year, and we can do it for the second period, and we bring the second period back to P. So now we have here P number 1, and we have P number 2, and then we have P number 3, P4, and P5. So actually P total here will be equal to P1 plus P2 plus P3 plus P4 plus P5. And all what we did, we brought the future value of each one of these to the present. So I dealt with each one of them individually. So this is one of the methods to find present worth in this case. So if I would like to see how it's been done, then I did bring the 1000 as a future value to year 0, which is the present, and this will be the principal, or P1. So this is P1. Now this one is P2. This is P3, P4, and P5. Adding them together will get, or will give us the present value, which is this one, the total present worth value, and that will be $5,204 and 3 cents. $5,204.03. And this is the first method. For the second method, the second method is dividing the series of payments into one that's equal. So we have equal payment series, and each one of them is 1000, and another one is a gradient series with 250, the G amount equal to $250. Notice that for the gradient, year 1 will be 0 and start growing or changing from that point. So it will be 250, 500, 750, 1000, and so on. So this will be the gradient, and this will be the equal payment series. For the equal payment series, we will use the equal payment formula. P is equal to A multiplied by the factor P given A with 12% rate and 5 years the number of periods, and that will equal to 3,604.80 cents. Now for the gradient, we use the gradient, and this is G, so we use the formula for the gradient, and this will be G, which is the 250 multiplied by the factor which is P given G with 12% interest, and 5 is the number of periods for this series, and that will be $1,599.20. Adding the two will give us the total present worth, which is $5,204.28, which is almost the same as the other one. A few cents difference will not make that much of a difference. But as you can see, it's been calculated in two different methods. The first method, which is just returning the future value into present and adding these present value together, and you will get the total present worth. The other way, or the other method, is using the gradient. So we separate equal payment series from gradient series, and we calculate the two values, then we add P1 plus P2. Let's look at this example, and in this example we are looking at the option of taking the lump sum of a lottery at the present, or taking it over the years with annual payment and gradual increase of $7,000 every year. So G is equal to $7,000. If we look at that, we can find that we have equivalent payment or equal payment of $189,000 every year, but for the first year it's separate, which will be $175,000, and after that we can say that we have $189,000 with interest rate of 4.5 over 25 years, and gradient amount, which is the 7,000, that can be brought into year 2, and then from or can be brought to year 1, and from year 1 back to 0 using interest rate 4.5%. So we can bring the this value, which is the gradient value, we can bring that to year 0. So the gradient amount will be returned as a value from the future to present with a 4.5% for 1 year, and that's to just bring the value 1 year back. You can create an Excel sheet to make the same calculation and to look or monitor over the 25 years what will happen with the amount of money that's been paid or saved. Another non-equal payment example is the geometric gradient series. And the geometric gradient is a gradient series that is being determined by a fixed rate expressed as percentage instead of the fixed dollar amount. In the first one, we said that we have a G amount, uppercase G, that represents the money increase, and that those are the equal gradual either increase or decrease in the amount. While in this case we are talking about more of a percentage. It's a percentage increase, not a dollar amount increase or decrease. The constant percentage will be 1 plus G and in this case it's lowercase g. So the gradient percentage, we refer to it as lowercase g, and it will be calculated as 1 plus g, which is as an interest, to the power 1 or to the power 2 to the power 3 all the way to the power n periods of time. And that's of course showing the increase or decrease in the amount. To find the present worth, we can use either the first formula, which will be used when I does not equal to g, if the interest rate is not equal to the gradient rate. If the gradient rate is different than the interest rate, then we use this formula. If the interest rate is equal to the gradient rate, then we use the second formula, or this formula. The factor in this case, which is the 1 minus 1 plus g to the power n multiplied by 1 plus I to the minus n divided by 1 minus I minus g. This factor is called the geometric gradient series present worth factor. The geometric gradient present worth factor. And of course, like we said, we have two different factors. This factor in case that I does not equal to g, and this factor in case that I is equal to g. If we let g prime or g dash equal to I minus g divided by 1 plus g, then the present worth will equal to a1 divided by 1 plus g multiplied by the geometric series factor using the new percentage, which is g prime or g dash. So we can use this formula to find the present worth. Let's look at the following example. We need to find the present worth if we have g is equal to 5%, I is equal to 7% over 25 years with annuity of $50,000. Now notice that g is not equal to I, or I is not equal to g. I is equal to 7% while g is equal to 5%. Since this is the case, then we use the first formula and we calculate using the a. So we have p is equal to a1, in this case it's 50,000, multiplied by the factor, and that will give us $696. So now we can calculate, using the annuity or the payment, the 50,000 over the 25 years with 7% interest, and we subtract that from the gradient series. So the difference will be $358,017. And this is the difference between what you pay out of pocket, 50,000 every year, that's out of pocket, and what you get back in a gradient series if you are saving. Or if it's the other way around, then the payment that will be given to you is 50,000 if the gradient series that is taken, which is the 940,000. And that's how we calculate the difference between what's coming in and what's going out, the inflows and the outflows, based on the series that we have, or the payments that we have. That will be all for the gradient series. If you have any questions, you can email it to me. Thank you and have a great day.